The overall goal of electronic time-resolved scanning tunneling microscopy is to study dynamic processes occurring on the atomic scale. In these experiments, the charge dynamics of dopants in silicon are studied.
These methods can be used to investigate interesting phenomena in the field of nanotechnology and physics, such as the rate at which dopants in semiconductors are supplied with electrons, or how tunneling current can be used to drive the magnetic resonance of individual atoms.
The main advantage of these techniques is that fast dynamics can be studied without the need to integrate optics into the tunneling junction.
These techniques are not limited to low temperatures or ultra-high vacuum scanning tunneling microscopes.
To begin, cool a scanning tunneling microscope capable of ultra-high vacuum to cryogenic temperatures. Ensure that the microscope's tip is equipped with high-frequency wiring capable of about 500 MHz. Then, connect an arbitrary function generator with at least 2 channels to the tip. Prepare the cycles of voltage pulse pairs used for pump probe experiments by configuring the arbitrary function generator so that the pump and probe voltage pulses are generated independently and summed before being fed into the tip. Next, apply the DC bias voltage used for imaging and conventional spectroscopy to the sample. Then, connect 2 radio frequency switches to the arbitrary function generator's output channels. Configure the switches so that the tip will be grounded during scanning, tunneling, imaging, and conventional spectroscopy. Collect the tunneling current for all measurements through a preamplifier connected to